Hi, this is Professor Cummings, and I have another problem I want to work through with you. And this one is a CAM problem, but still in the mechanical design playlist. So we go through CAMs, linkages, and planetary gearing all inside of that playlist. But to get to this one, we want to see this particular diagram. And I like this one because it does show fundamentally some of the things about CAMs without going into all the things such as harmonic motion and all of the details, but some ideas to just how the cam physically moves. So you're going to see in this problem rotary motion. Let me change my pointer. Let's see, here we go. We're going to see the rotary motion of the cam. In this case, it's going to be going counterclockwise, and the translational or linear motion of the follower. And you see a spring loaded, so it has a natural position back here at point C. And as the cam rotates clockwise, it's going to be going, forcing the follower left to right. And let's see, determine the velocity and acceleration, that's linear velocity and linear acceleration, of the follower rod, which is CD, as a function of theta. Theta is the rotary displacement, angular displacement of the cam, when the contact between the cam and the follower is along the straight region AB. So here is AB, this straight region, so we want to know what's going on as it travels through this region AB. On the face of the cam rotates with a constant counterclockwise angular velocity. Alrighty, so again, we look at the cam, it goes from C to D. It runs along this straight line here, and it has this perpendicular point going to the origin from A to O. And that also has a distance of R. That's going to become important. And we're looking at it at the end at this angle of theta, which basically, again, is just where it displaced at any point in time. Again, constant velocity, angular velocity of omega. Alrighty, and as you need, the principle behind the cam is to take rotary motion and translate it into linear motion. So let's see here. So that's what we're concerned with. And you can see, like I said, this is a right triangle. Again, that's going to become important as the equation goes on, and we're just concerned with the rise portion. That's known as the rise portion of the cam. And this is the direction that the follower is going to take. So let's see. So AOC is a right triangle. O to C, 0 to C, is the hypotenuse of that triangle. And the follower is moving in the positive x direction. So since we're taking a rotary motion and we're trying to relate it to something going in a linear motion, we're going to have to come up with several relationships between that cam motion and the follower's motion. We're also going to need, because we're looking at that right triangle and we're trying to understand theta, we're going to need to understand some relationships, some identities between some trig identities, as well as some reciprocal identities that's going to come into play here, especially as we take some derivatives. We're going to need some derivatives. We're starting off with displacement. We're going to be looking at velocity and acceleration. So that's what we're going to be preparing for. So when we look at this, we're going to go back to this relationship. We've seen this in a couple of videos of displacement of S and theta, and how in both cases, the derivative with respect to time gives us omega or velocity, angular velocity or linear velocity, and that second derivative gets us angular acceleration or linear acceleration. We also have derivatives of several trig functions, and we're going to see several of these pop up. And then we're also going to have several reciprocal identities as we go through this problem. We're also going to go through the chain rule as well as the product rule as we work through this. So again, I brought these here, tried to put them as well into the position as we could, and we're going to go through and going to first look at how we can identify the displacement. We'll start off just up in this area. So if we look at this, we can try and get that displacement of OC, that distance from O to C, and make a relationship of there as R over the cosine of theta. All right. So that's just SOHCAHTOA. So again, this horizontal is the cosine of theta, the hypotenuse, divided by R, and that distance OC. And again, because we have that reciprocal identity, we can know that R over cosine of theta is actually equal to the secant of theta. To make this a little easier to deal with because of what we're going to have to do next, or eventually. So we got the distance can be calculated by the radius of the follower, or radius of the cam, times the secant of theta. So that's the best way we can identify what that hypotenuse, that distance of the follower is. Now we're going to come up with the velocity. So we're going to need to actually take a derivative of the velocity, as well as, because we're dealing with the secant, we're going to have to take the derivative of that secant. So that secant of x, or secant of theta in this case, is equal to the derivative, the secant of theta, is equal to secant of theta times tangent of theta. So when we do that derivative to end up with what the velocity is, the derivative of this displacement. And since that R is a constant, that R is going to be a constant value, that's going to come outside the derivative. So if we can say what the linear velocity will be, it's the derivative of the displacement with respect to time. So R times the secant of theta times the tangent of theta. Remember, we got to do with the chain rule. So this is the derivative of the outside times the derivative of the inside, which is the derivative of theta with respect to time. And this is angular velocity. So again, we're dealing with angular velocity at that point. So we can simplify this as R times the angular velocity times the secant of theta times the tangent of theta. So this is a function that tells us the velocity of the follower at any point in time going down this straightaway of AB. So that's the first part of the problem solved. Determine the velocity of the follower. Now we've got to do the acceleration of the follower. So in order to do that, we're going to need this identity, the derivative of the velocity. So in order to do that, we're going to end up having to take the product rule, but it's going to be a compounded product rule of basically delta theta with respect to time, or omega, times the secant of theta times the tangent of theta. So, and then there's going to be the chain rule on top of that. So velocity, derivative of the velocity with respect to time, or acceleration. This R is a constant, so it comes all the way out to here. Secant of theta times the tangent of theta times alpha, angular acceleration. So that's the derivative of the omega. Plus, this is the product rule. Again, this angular velocity is going to come outside of this because we're not going to take this derivative in these next two motions. Again, secant of theta, again, times the derivative of the tangent of theta, which is also going to have the chain rule. So we got another second omega. So secant squared theta. So if we look over here, the tangent of theta is the secant squared of x. So here we got secant squared of theta, secant squared of theta times omega. That's the chain rule and the product rule. Plus, again, the next part of the product rule, which is the derivative of secant of theta, which is, again, tangent of theta, secant of theta, tangent of theta, again, which is, again, this one over again, times omega. So now we're going to have a pretty messy calculation there, but it'll get a little cleaned up here. For one, we're going to be able to factor out, all those omegas, and we've got another piece of information here that's going to become very important in that simplification. So to simplify this acceleration, again, once we start to simplify this, the secant theta times the secant squared gives us secant of theta cubed, plus secant of theta times tangent squared. We these two tangent of thetas. And then we've got omega squared. Now, another piece of information, it is a constant angular velocity, so the angular acceleration is 0. So we'll just clean up the board a little bit here. Constant counterclockwise angular velocity of omega. So our angular velocity is 0. Alpha is going to equal 0. So this drops out. So it becomes a little simpler to look at. So the linear acceleration of the follower is r times omega squared times the quantity of secant cubed theta plus secant of theta tangent squared theta going towards the right. So that is a really good example, a really good illustration of that translation of angular velocity to translational or linear velocity. And we'll probably start doing a few more videos here on CAMs as we move forward. But thanks for watching, and don't forget to like, comment, and subscribe. Share this, particularly if you're in a semester where you're doing this. This might, be helpful to some friends or helpful to some of your classmates. But again, also remember, you can always just reference this one as you need to. So this is Professor Cummings, and I'll talk to you soon.